Our last topic for chapter 18 is electrochemical cells. So in these cells, oxidation will occur at the anode, reduction at the cathode, just like in voltaic cells. But in electrolytic cells, we are adding energy in. So electrons are drawn off the anode. It needs to have a place to return, which is the positive terminal of the battery, and electrons are forced toward the anode. So it has a source of electrons as well. So here's a picture. We've looked at this picture multiple times where our electrons are flowing from the solid zinc through the aqueous zinc to the aqueous copper, then to the solid copper. Here we are running it in reverse. So we have forced the reaction to go backwards by adding a voltage source. Electrolysis is using electrical energy to break a compound apart. So we can do that in an electrolytic cell. And one thing it's especially useful for is separating elements from their compounds. So for example, we can run a battery through water and separate the water into oxygen and hydrogen. Basically, we are using electrical energy to overcome that barrier for a non-spontaneous reaction. And so in electrolysis, whatever reaction we're looking at is the opposite of the spontaneous process. This can be widely applied to things like metal extraction from minerals, production of hydrogen from fuel cells, and metal plating. We use a battery. We kind of talked about all that. If we're using pure compounds, the compound needs to be in its liquid state. Cations are reduced at the cathode to the metal element, and anions are oxidized at the anode to the non-metal element. So, for example, if you wanted to make sodium chloride into sodium and chlorine, you could use electrolysis for that. Here's the picture. We have some molten sodium chloride. The chloride is oxidized to chlorine at the anode, and the sodium is reduced to sodium, elemental sodium at the cathode. For electroplating, we can do something like put a silver anode in at our voltage source and then put an object to be plated. So for instance, if you go to get a silver or gold ring cleaned, they will often electroplate it for you. Just add a new layer on the outside. And at the anode, the silver in this case is being made into aqueous silver ions, and then those ions are electroplated onto the ring there at the cathode. Now, when we have a mixture of ions, the cation that is easiest to reduce will be reduced first at the cathode. When you have more than one anion, the anion that's easiest to oxidize will be oxidized first. So again, we're going to be referring back to our table 18.1. So predict the half reaction occurring at the anode and cathode for the electrolysis for a mixture of molten aluminum bromide and magnesium bromide. So our oxidation reaction, we have bromine for both of them. So our oxidation reaction is going to be bromine going to bromide. We need a 2 here. So that's our oxidation. Our reduction, we have 2 choices. We can reduce our aluminum 3 to solid aluminum, or we can reduce our magnesium to solid magnesium. We can look up the values, and here we see our value for our aluminum, if you look it up in the table, is negative 1.66 volts. Our potential for our magnesium is negative 2.37 volts. The aluminum has a more positive or a less negative potential, so our aluminum will be reduced first. So here, aluminum has a more positive value, so it's easier. Next, predict the half reaction occurring at the anode and cathode for the electrolysis of a mixture of molten magnesium chloride and magnesium bromide. So our reduction is definitely going to be the magnesium plus 2 electrons goes to magnesium solid. But then we have to compare our chlorine and our bromine. And again, we can look those up in the book. And we have negative 1.36, negative 1.09. And so the one for bromine is lower. And so that is the one that will be reduced. It's the least negative, easiest one for it to happen. It's also important to keep in mind, if you're working in aqueous solutions, that you could also just react your water. The reduction of water to hydrogen has a standard potential at negative 0.83 volts. If we're at pH 7, it's negative 0.41. Or we could oxidize our water to oxygen, which has a standard potential of negative 1.23 volts. Also, keep in mind, you could, in theory, oxidize your electrode. Copper, in particular, is something to watch out for, but graphite won't oxidize. And any half reaction that leads to the least negative cell potential will occur. So these water ones especially are something to keep an eye out for. Okay, so predict the half reaction occurring at the anode and cathode for the electrolysis of sodium bromide. So our choices are sodium plus an electron goes to sodium metal. And from the previous slide, 2 water plus 2 electrons goes to H plus 2OH. And my cell potentials for that one, I can get from the previous slide. It's negative 0.83 volts. And for my sodium, negative 3.04 volts. So this is the one that's going to occur. Then for my other reaction, my possibilities are, this is going to be 2 bromides, goes to Br2 plus 2 electrons, or from the previous slide, 4 water goes to 2 oxygen plus 4 electrons plus 4 protons. Sorry, that's 1 oxygen there. And my value here is negative 1.09. So assuming we're under standard conditions, this reaction will occur. If we're at pH 7, my value here drops to negative 0.82. So at pH 7, then this one will occur. So that's going to be pH dependent. So on this slide showing my answer, it's looking at we're at pH 7, but it doesn't say that in the question. So, all right. We can also figure out the stoichiometry of electrolysis. The amount of product made is related to the number of electrons transferred. So we can basically set up a big dimensional analysis problem and figure out the number of moles of electrons and the mass of product that we get depending on how long we run the electrolysis for. So you need to know that 1 amp is 1 coulomb per second. 1 mole of electrons is 96,485 coulombs of charge. So we'll look at an example like this. I did this one backwards. Calculate the mass of gold that can be plated in 25 minutes using 5.5 amps for this half reaction. So we're going to start with our 25 minutes, convert that into seconds. So 1 minute is 60 seconds. Then we're at 5.5 amps, and an amp is 1 coulomb per second. So 5.5 coulombs per second. Then 1 mole of electrons is 96,485 coulombs of charge. Then for every 1 gold, we are using 3 electrons, so 3 electrons per 1 gold. And then we know where we can look up these are both moles. The molar mass of gold is 196.97 grams. So I converted my minutes into seconds, my seconds to coulombs, seconds to coulombs, my coulombs to moles of electrons. Then I use my balance equation to go from moles of electrons to moles of gold, then moles of gold over to grams of gold. So if I do all of that math, I get 5.6 grams of gold. All right, here's another question for you to practice. This one's a little bit different. Calculate the amperage required to plate 2.5 grams of gold in 1 hour. So we want 2.5 grams in 3,600 seconds. We can use our molar mass. So 196.97 grams is 1 mole of gold. Then we know that for every 1 mole of gold, we have 3 moles of electrons, and 1 mole of electrons is 96,485 coulombs, and amps is coulombs per second. So if I check my math here, grams, moles of gold, moles of gold, moles of electrons, I'm left in coulombs per second. So if I do all of that math, I'm going to end up with 1.0 amps.